everybody for joining us this week. We're having some technical difficulty with mics, but I think yours works. Yes, maybe. Yes. Maybe. Okay, good. So this week we're very happy to have Graaff talking about some of her work. And I did her PhD in Leiden and then came to MPIA as a postdoc. And we were very lucky to catch her before she leaves town in the fall to go to a Hubble and Clay Fellowship at the CFA. So we very much thank you.
Thanks. Yeah. Thanks for having me, and it's fun to be on the other side for once here. I'm gonna try to stand close to my own laptop so that people on Zoom can hear, but we're in a precarious microphone situation over here. So today I want to really celebrate 3 years of JWST, and I want to expand first. As I was putting together these slides, I realized that my own timeline coincides somewhat with that of JWST as well, or aligns, I should say. And that is that people started designing this telescope actually when I was born. But more seriously is that I joined the NIRSpec GTO team back in 2018 at the start of my PhD. And that also actually coincided with the last major launch delay of JWST. So it was postponed to 2021 and then later, the end of 2021. And so that was a disaster for many people actually, but for me, it actually was pretty good. So if we look, because it meant that I could spend a few years actually learning how this instrument works and also learning how galaxies work. So I actually spent my thesis focusing on massive galaxies in the late time universe. And then as I wrote up my thesis, actually the first data from Webb started coming in. And my time at MPIA has therefore been spent purely on JWST, focusing on really the progenitors of these massive galaxies that I studied all these years. And we know that the progenitors of the most massive galaxies must have been in this very, very early phase of the universe, so redshift 10 or so, because when we look in the local universe and perform these archaeological studies of massive galaxies, we can reconstruct their star formation histories. And when we do that, we see the following picture where the most massive systems actually formed between 50 to 90% of their stellar mass actually in the first 2 to 3 billion years. And so if you want to understand how massive galaxies grow, and by massive, I mean galaxies as massive as the Milky Way or more, then we need to go to this very early epoch, but we know actually surprisingly little about this very early ramp up in stellar mass growth. And before I jump into all the things we've learned and all the surprises we've seen with JWST, I just want to briefly show where we were before in 2021, and so you can understand why these surprises are actually surprising. And so I'll start by showing a video of a simulation. This is actually from the FIRE simulations showing a pretty high resolution zoom in of a Milky Way mass system. And it starts at a redshift of 99, so very, very early in the universe. And then you'll see slowly how a Milky Way-like galaxy forms. I'll just say in advance, there's only stars, gas, and dark matter in the simulation, so no black holes. And what you see is that early on, there's all this gas falling in, where stars are then formed in a very chaotic way. So stuff falls in, is also blown out again by feedback. And it's only around 2 billion years after the Big Bang that you start to see in the center this disk-like structure forming. And it's only really it takes a few more billion years to actually start to see that transform into a disk where you look at it and you say, okay, that's actually a disk. And then it takes another several billions of years before you start to form something that actually looks like our own Milky Way. And this video will only play until redshift 0.5, because actually there's not a whole lot happening in this particular simulation. But this kind of sets the picture, right? We have this chaotic phase at the start, and then gradually build your galaxy. And this is also what we see in our observations. So if we look at Hubble imaging, for instance, we can see how galaxies actually assemble in mass. What we find is that at lower redshifts, we have a lot of these disks, especially at the massive end. And towards higher redshifts, galaxies become increasingly clumpy and kind of irregular in their morphologies. And we quantify or we call these kind of elongated systems, which occurs particularly at higher redshifts and at lower masses. Despite looking clumpy, though, a lot of these systems are already kind of rotating. So if we take IFU cubes of these galaxies, just from ground-based spectroscopy, you see a lot of these are actually rotating disks that are not just rotating, but they're also baryon-dominated disks, so they're full of stars and gas. So the picture you need to have in mind is that we have these pretty thick disks at redshifts sort of 2 to 3, so it's a few billion years after Big Bang, that are the progenitors of massive galaxies today. And there is a lot of star formation occurring in things that are roughly diski, but there's still a lot of turbulence in these systems. We did know there were some galaxies that did not align with this picture. So there are these oddballs where you see these very, very compact red galaxies that look nothing like the disks I was showing you before. And this tells us that something weird is happening in the first few billion years. And so these galaxies in particular, these are very massive systems that must have formed in very rapid bursts of star formation. And they didn't only form in a rapid burst, but actually also then stopped forming stars in an epoch where normally star formation is only ramping up in the universe. So we knew something was kind of afoot in the early universe. We also know this from other more statistical studies, where if you look at the kinematics, the disks become more and more turbulent towards higher redshifts, even at the high mass end. And in general, the velocity dispersion of the ISM increases towards earlier times. Okay, so to recap, this is sort of our picture that we have, right? Where if we want to see how a massive galaxy formed, then we expect the first few billion years to be very turbulent with a lot of star formation. And then Webb came. And as you might know by now, is that JWST, well, it looks like this, you for sure know that. But there are 4 instruments on board JWST. And the sort of the workhorse of JWST is definitely NIRCam. So that's the NIRSpec imager on board JWST. And in its first year, it delivered what we call wide area imaging. So it's around 700 square minutes, but at extreme depth. So up to the 30th magnitude in AB. So it's several magnitudes deeper than Hubble imaging and across pretty wide area. So it's really impressive. What is even more impressive is actually the spectroscopy that has come out of JWST. And in particular, NIRSpec, of course, I'm biased because I'm on the GTO team, but NIRSpec is incredible for several reasons. And that is, it's extremely versatile. So it has multiple modes, multiple resolutions, so you can really resolve all sorts of characteristics of galaxies or planets or stars, whatever you're interested in. And it is, even though there are many instruments on board JWST, it is the most sensitive by far on board of all instruments on board JWST. And I'm particularly interested in the multi-object spectroscopy mode, because what it allows you to do is to observe 200 galaxies in one go in just a couple hours at this unprecedented depth. And this mode is enabled by this scary looking equipment that's called the microshutter array. So these are essentially little doors you can open and close to construct little slitlets. And where normally you design, if you design a space mission or a satellite, you minimize the number of moving parts. Well, NIRSpec is happily floating in L2 with 250,000 moving parts. And somehow this works, right? So where for most people, their favorite commissioning image is something like this, where you see the improvement over Spitzer with Webb and sensitivity and resolution. Actually, my own favorite commissioning image is this, where you see the zodiacal light, which is great, but dispersed 200 times on the detector. And this came out about a month after I accepted this job. And I realized that I actually had something to work with here. And since then, we've just been taking data almost nonstop. So there are several large spectroscopic surveys that we've conducted with this instrument. Several I've been involved in or led myself. And they all cover slightly different parts of parameter space, so galaxy parameter space, but also cover different areas at different depths. For the purposes of today, I'm going to focus on 2 of the outliers here. So that is the very deepest data that we've taken, but also some of the shallow or JWST shallow wide area spectroscopy. And with all this data, we've been studying all sorts of aspects of galaxy formation, but it all comes out, all these different discoveries that I'm about to show you all kind of point to the same overarching conclusion. And that is that we find actually that galaxies grow and mature very rapidly in the first few billion years. And this manifests itself in very different ways. And I'll highlight sort of 3 of these aspects today. There's actually a 4th that I won't talk about, it's chemical evolution, but they all point to the same picture. And I'll start with just the morphologies themselves, where I showed you before that with Hubble, we saw these galaxies that look extremely clumpy at higher redshifts. But if you look at the exact same systems, even at the same wavelengths with JWST, you see that what looked like clumps before are actually very well-organized spiral arms embedded in these very smooth underlying disks. And we see these disks everywhere, no matter how you search for them. So if you do this by visual inspection through, for instance, the Galaxy Zoo project that's now done this for tens of thousands of systems, or if you apply your favorite machine learning methods to search for these, or if you apply parametric morphological modeling in a similar way as we've done before, then you actually can compare directly to our previous Hubble measurements. And what you see is that the disk fraction is extremely high, much higher than we expected even from our previous observations. And this is interesting because it actually tells us that star formation is different, right, in the early universe from how we thought. So it means that star formation occurs in these regulated rotating disks, maybe. And I say maybe because, of course, this all looks disky. And by looks disky, I mean it looks kind of smooth and, you know, it looks a little bit flattened. But there are many ways to get actually a system like that. So it can truly be a rotating disk, but you can also have these sort of elongated systems where you essentially have inflow of gas producing a morphology that looks kind of like this. And the only way to distinguish between these two is to take spectra and actually look for signatures of rotation. And this is exactly what we've been doing in the GTO survey. So the NIRSpec GTO is very nice because it actually looks at the same galaxies with all the different modes. So it means you can get at the same time very robust stellar masses, but also a very good picture of the ISM, and at the same time also the kinematics for these high redshift galaxies. And all at a very, very high depth. So some of these observations are like 30 hours or even up to 100 hours. And what we saw in these systems is, so this is looking at high resolution data. So if you look at some of these galaxies that look kind of disky, so pretty smooth in the NIRCam imaging, and you disperse it, is that you see these rotation curves or like velocity gradients, I should really say. So there's one spatial axis here and one velocity axis. And you see they're kind of tilted. And what is incredible about this is that we see ionized gas kinematics in action at redshift 7 in this case. But it's not just that we are going to a different redshift range, we're also actually probing a totally different regime in terms of stellar mass and size, right? So we're really probing the smallest galaxies that are really the building blocks of the more massive galaxies later on for the first time dynamically. And I'll kind of gloss over how we actually then go from the spectra to inferring kinematic properties. I'll just say that I spent a lot of time on it because it's not trivial how you actually go from a spectrum with only one spatial dimension and one velocity axis to useful parameters. So we do this full forward modeling approach to, in the end, essentially extract a rotation velocity and a dispersion, and based on that also a dynamic. And what this showed us is that the dynamics of these high redshift galaxies are actually much colder than we would have expected. So if you look at redshift sort of 1 to 3, where we have all this ground-based data, then you expect the velocity dispersion to kind of keep on increasing towards earlier times, so the galaxies become more turbulent. But what we actually see is that they're not more turbulent. The velocity dispersion is kind of the same as at lower redshifts. And we also see this when we look at this ratio between the rotation and velocity dispersion. So this is V over sigma, where if you extrapolate essentially the lower redshift data points, you would expect none of our systems to have V over sigma is greater than 1. But we actually see this diversity, which implies that we probably have some rotating disks at these very, very early times, in contrast with what we might have expected for the ionized gas, I should say. Now, the biggest surprise probably that came out of the dynamics, though, is not in this, but actually in the masses themselves, where normally when you have a galaxy at, you know, anywhere from redshift 0 to 3, the dynamical mass that you get out roughly equates to the baryonic mass at the center of the galaxy. So that's the stars and the gas itself. But what we find in these galaxies is actually that the stellar mass makes up only 2% of the total mass. And even if we also include gas in this mass budget, we still have a factor 3 to 4 that we need to explain somehow. So there's this systematic discrepancy between the total and baryonic masses in these galaxies. And this is actually really surprising because it's not at all what we expected from our observations. And there are different explanations. One of them being that, you know, you might have just gotten, well, lucky or unlucky, depending on how you look at it. So if you have merging systems, then you can actually overestimate your mass somehow. And it's only a small sample. But as well, Jakob will tell you in the audience, we've now been doing this also for several thousand galaxies. from redshift 1 to 7. And what you see is that if we compare the y-axis here is roughly dynamical mass and the x-axis here is stellar mass. And what you see is that beyond the stellar mass of 10 to the 9, there's a pretty good correlation between dynamical mass and stellar mass. So this picture that the baryons make up the entire galaxy. And then there's this flattening at the low mass end. And this seems to be real, or at least I'm convinced it's real. Jakob's not yet convinced, I think. But and what is there are different, again, there are a few explanations still left. So one of them is actually that you can have a lot of outflows in these systems that essentially drive the kinematics. But the other possible explanation is that you just have a lot of dark matter on these very, very small spatial scales. So on spatial scales of sort of 500 parsec to a kiloparsec. So yeah, we see this actually at all, which I should have expanded the figure. And interestingly, this is actually what simulations also predict. So if you just overlap sort of the measurements from JWST from my early paper with what TNG50 predicts on these very small spatial scales in redshift 6, then they align almost perfectly. And I think the physically interesting part here is that this could help to explain why we also see these rotating disks. Because if you have essentially a deep enough potential or a concentrated enough potential, here provided by dark matter, then you're also able to sustain a stable disk, which in turn is actually able to sustain then pretty efficient star formation. And so this all kind of points to a picture where galaxies actually grow pretty rapidly early on, and they're not able to form disks, which in turn then drives actually pretty efficient star formation and star mass growth. There's still quite a few ifs and buts here, but I think this is sort of the physically interesting picture that we're trying to work towards or disprove if needed. So the second major surprise is, I think, what took over really my life in the past year and a half. And that was the finding of very massive galaxies. And again, this started by comparing just Hubble data to JWST data. What we found is that all these systems pop out of the JWST imaging that we never saw before, not with Hubble and actually also not with instruments like Spitzer. And so we see them in all sorts of shapes. I was going to say shapes and colors, but no, they all have the same color, but they have different morphological properties. And what is interesting about the fact these galaxies are so red is that they're not just distant, but they're actually red in their rest optical. So it implies usually very high stellar masses. And so this is probably the most controversial paper that came out in, well, maybe even up to today from JWST. So it's from Ivo Labbe, where he found these very red compact sources about 1 billion years after the Big Bang. And he made a composite SEDs that's in red here. And what you see is this very strong rise in the rest optical, which could be consistent with the Balmer break, or in other words, evolved stellar populations, massive evolved stellar populations. And in green, you see sort of the typical SEDs that we found before with Hubble and Spitzer. So these are very low mass blue star forming systems. And the contrast in mass here is really extreme, because this would mean that these galaxies are an order of magnitude, or maybe even 2 orders of magnitude more massive than what we expected. And this has major consequences for all our galaxy formation models, where this really took off after someone pointed out that to make a galaxy this massive, and you need to keep in mind that we've been looking at pretty small fields, so that means that these galaxies are pretty numerous, and so they cannot live in very massive halos. And so what it implies is that if you don't live in very massive halo, you still host a very massive galaxy, then every single baryon in your halo needs to have been converted into a star. And that is something that none of our star formation models can do, for hopefully obvious reasons. And so this prompted some people to then say, well, if this is really true, then this means that our cosmological paradigm is actually also no longer holds, right? So that there's actually a problem with lambda CDM. Now, of course, that's a very major statement to make on the basis of 8-band photometry of a couple of galaxies. But nevertheless, by now we have many more of these extremely massive galaxy candidates. Some actually that you couldn't even explain with all the baryons in the universe. So clearly there's something wrong here, right? And like I said, we're all doing this based on photometry, which is great. Photometry is high quality photometry, but at the end of the day, it's still 8 filters. And it means that the redshifts of these galaxies are uncertain, but also the masses of these galaxies are extremely uncertain. And here are sort of, this is a counter paper essentially showing that with 3 very different models, you can explain the same SED shape. So essentially a star-forming galaxy, a very old galaxy, and then these very weird AGN models can all explain the same photometry that you see. And so people actually believed the most in this model on the right, which is honestly really crazy. It's something that we don't see in the local universe either. But so it was clear that we needed spectroscopy. And this is where my own program really came in. So this is the RIBIs, where the R and the U stand for red unknowns, and the other letters you can make up yourself. So this is a program with cycle 2, with about 30-ish people spread across Europe and the US, CoPI, Gatebremmer, and Dawn. And what RIBIs did was to survey essentially the high-redshift universe, but by focusing on the reddest galaxies. So we performed a pretty wide area survey because these red galaxies are kind of rare. And overall, we target about 5,000 systems. And we don't just observe the very reddest galaxies, but at the same time, we actually probe also the blue galaxies so we can actually compare them to each other. And we do so, this sounds easy, but actually very hard, and it's with a well-tractable selection function. And what you can do then is also actually stack these or sort these spectra from red to blue. You see sort of different features pop in and out. So the emission lines are very strong in the blue end, but the Balmer break becomes visible only in the red end. And what we ended up with is a survey that really probes something really different from all the other programs. So where the GTO focused really on the faint blue ends, really the highest redshift systems. What you see here, the polar magnitude spaces that we target as the only ones really this very large sample of these very red sources. So it's really a different parameter space. And in this parameter space lie a lot of gems or surprises. And the first that we found is actually this unambiguously massive system just a billion years after the Big Bang. And so what you see here is this massive quiescent galaxy where you see a strong Balmer break, rest frame 4,000 angstrom. And then you see these very strong absorption features. And that's a telltale sign of essentially A stars. So what this means is that you have a very evolved stellar population. It's actually very massive, but it has also shut off star formation in the most recent 100 million years or so. And the existence of this source by itself is actually already hard to explain or to accommodate in galaxy formation models, but it gets more extreme when we actually infer the star formation history of this source from the spectrum. And what you see then is this purple curve here, where if you model the spectra with our typical stellar population modeling that we've worked on so long for decades in the local universe, then you infer this formation history at redshift 10 as an extreme burst of star formation. Right, with star formation rates nearly 1,000 solar masses per year. And in turn, what this implies is if you convert, again, this number density or sort of the frequency at which we see these galaxies, if you equate it to a halo mass, then you can kind of get an estimate of how many baryons in a halo need to be converted into stars in order to make a galaxy like this. And what you see is that a galaxy like this would be very problematic, right? What you also see is this blue curve over here, which essentially captures the model uncertainty that we have. So I say models are calibrated in the local universe is actually also a problem. So this blue curve is something you can see as the youngest possible solution for this galaxy to be formed, and you still need this very, very extreme burst of star formation with a star formation efficiency that's not breaking lambda CDM in any way, but it's still extremely high, right? So it's beyond actually the peak of the stellar to halo mass relation at redshift 0. And we don't just find one of these, we found more of these. So there's one that's even higher redshifts, Andrea Bible, where again, you see a bit noisier, but you see this very strong Balmer break followed with some absorption features. And what is nice about this source is that it's extremely compact. And it's in fact so compact that it's as dense as some of the star clusters we see in the local universe. And actually, it's as dense as the very cores of today's local elliptical galaxies. So we're actually seeing the formation of the most massive galaxies happening, at these very early epochs. And these are just 2 galaxies. By now, we have actually a few dozen. And Yuncheng Zhang has put this together into a number density estimate and made a detailed comparison to multiple galaxy formation models. And what you see here is so 6 of the largest public galaxy formation models at the moment, together with our measurements. And you see that particularly at the highest redshifts, there is a very strong discrepancy between the measured number density and what you get out of the simulation of at least a dex and sometimes even more. And at redshift 7, this gets even crazier, where we're really 2 dex beyond what we might have expected to find. So this is clearly a problem. And now one of the ways out that people like to mention is, well, maybe you just got lucky, right? Like you're only targeting really 2 survey fields here. And, you know, if you have some overdensity, you know, cosmic variance is a big factor. And you might explain it away like that. But at this point, so MJ Park had a paper where the only thing to take away from this figure is that we have many of these systems. And we find them essentially in every field where we look with JWST. It doesn't matter which patch of the sky, you find systems that are very old, very massive, and very early universe. And so what this means is that cosmic variance is no longer sort of a cop-out, and we actually need to address this issue between our theoretical models and what we observe. And then I lead into the final problem. And this, I laugh because there was a HJAC colloquium a few months ago from Jenny Green on kind of the same topic. And I work very closely with Jenny Green. So I hope this is going to be, well, this is sort of the sequel to her colloquium. So you've probably heard about this phenomenon called little red dots. And these are probably the most debated sources in the literature at the moment. I think one of the reasons is because it actually brings together 2 communities. And I'll just say that as an extragalactic observer, I was tricked into this. And I'll tell you why, because it goes back again to this controversial paper where we found these very compact red sources where, you know, you have these different models that can explain it. And you should focus your attention really on the bottom, like the 2 on the right here, where in the center you see this model that has a very strong Balmer breaks. It's essentially this old evolved stellar population in the early universe. And on the right, you have this AGN model that explains essentially all the flux. And in Ruby's, we took spectra of pretty much all the sources in Evo's original paper, including sort of the worst offenders. And the results are probably even more puzzling than the photometry was. So we said we'll take the spectra, we wrote the proposal, we said we'll take the spectra and settle the debate. But, you know, it's actually a nice, it's still not settled. So the controversy is as follows. So we took spectra, and what we see is we see these strong Balmer breaks indeed, right? So there is one side of the debate here that still says, okay, we see these very strong Balmer breaks, and that implies we have these very evolved, massive stellar populations in the first few 100 million years. And this means that this problem of extreme stellar mass growth and, you know, this possible tension with lambda CDM has not gone away, right? And there's at least one side of the debate. But in the exact same spectra, we also see these very broad Balmer emission lines coupled with very narrow forbidden lines. And this is, of course, normally a telltale sign of type 1 AGMs, so these broad line AGM. And so the other camp, which is now winning, I should say, says, okay, well, I see these broad Balmer lines, so all your other stuff goes out the window. And I believe these systems are 100% dominated by just some luminous accreting black hole. This causes other issues, I should say, less severe, but still causes issues, because these little red dots only make up a small fraction of the total population of AGN. And just the population of little red dots already accounts for all the volumetric luminosity of black holes in galaxy formation models. So it means that you have then very extreme black hole growth in the early universe. You might wonder, you know, why do we need one or the other? Can we not just do a little bit of both? And this was, I think, a few months ago, at the time that Jenny gave her talk, I think it was still the favored solution. So you have something that is partially a massive galaxy, but maybe not as extreme, that it actually breaks models, and you have a black hole there, but not as extreme that you actually have tension with models either. But there are other issues there where that actually requires a very high degree of fine-tuning. So you need to have this population where you have everything be 50-50 in terms of stellar mass and sort of AGN-driven luminosity. And it's a pretty precarious setup. And also actually still implies that you need galaxies to be, so it's these red points here, you need galaxies to be sort of at the theoretical limit for how dense star clusters can be, or at the observed limit, I should say, not theoretical limit. So that means you have systems that are, a few hundred parsec in size, but as dense as some of our star clusters in the local universe that are less than a parsec in size. So you still need some very crazy physical setup, coupled with some very fine-tuned galaxies. And this is uncomfortable, especially because we don't find just a handful of these systems now, right? We actually find tons of them. So this is a paper actually that came out yesterday from Graaff and it's posted at the MPIA. And what he showed, he looked at all the Ruby spectra and he quantified, how many of these type 1 AGN do we have, or how many broad lines do we have, and then looked at how many of them actually qualify as a little red dot, so have sort of this Balmer break in them. And what you see is, this is a bit of a circuit ball, but what you see is that about half of the AGN that we find in our survey, we're biased to the brighter end, are these little red dots where, you have both a Balmer break and these very broad ones. And what this means is that if you want to have a fine-tuned solution, that doesn't work when you have a large sample of these systems. And we also find them out to, you find them across all redshifts and all sorts of magnitudes as well. So it simply doesn't. And so I think the big progress in the recent months has been actually due to a handful of sources that broke all our models and actually forced us to go back to the drawing board. And so I'll show you what I mean by that. So in pink here, you see one of these massive coalescing galaxies that I showed you earlier that are also actually still very, very extreme systems. So you see the strong Balmer break and these absorption features. And then I'll show you what little red dots look like. We would do something like this. So up to 4,000 angstrom, they mimic pretty well, our massive quiescent system. And then beyond that, you get this extra flux. So this how the composite models work as well, right? So up to 4,000 angstrom, you say everything is stars, and then beyond that, you need an AGN component. That's also why it's such a fine-tuned solution. And then we found a source that looks nothing like this, that actually just shoots up essentially at the Balmer limit. And this is really, it's hard to explain how extreme this is, but if you compare this to any other system we've really ever observed, I'm only showing redshift 3 and above here, but I think it still holds the statement even for like Sloan and like large spectroscopic surveys like that, where we've never seen a Balmer break this strong before. And what this means is that it's really beyond anything that a normal stellar population or a stellar population that we know of can produce. And so we resorted to all sorts of weird models instead. At some point, even resorted to looking at just individual stellar spectra, looking at, what sort of stars, if I had a delta function IMF and I allowed for, the most extreme stellar model, could I explain this galaxy? And the answer is no. So, the most extreme, so in dotted lines here are simply stellar spectra, and solid here are after attenuating by some very extreme dust lulls. And when you see that essentially none of these stars, so A stars typically make the strongest Balmer breaks, none of them actually come close to matching this spectral shape. And at that point, you need to wonder, okay, what am I actually dealing with? And I think this was good because it actually forced us to step away from all this precarious modeling we tried to do before and simply take the data at face value and ask, what is it actually telling me? And so we see this strong Balmer break, sure. And what this means is you have some gas that's at the right opacity to essentially produce it, right? So you need to have enough hydrogen that's in this n=2 state. We also see this Rayleigh-Jeans tail. So you see that the near infrared is pretty blue and it's dropping off with essentially a parallel slope to -2, which is something that normal AGN don't do, right? So normal AGN have hot dust typically, and they will rise again in the near to mid infrared. So, okay, that's another piece. And then the third is that these emission lines, so these H-alpha lines that we see, are extremely bright, and their profiles are kind of funny, where they're actually not Gaussian in shape, but they're actually Lorentzian in shape. And if you look closely enough, then actually a lot of them have this very subtle dip in them in the middle, not quite in the middle, slightly offset, which is an absorption feature. And to get absorption in the Balmer lines requires very, very dense gas. And so what this all points to is that we need some sort of really dense gas around some sort of ionizing source without making any qualitative statements about what that should look like or how you even would make such a system in the first place. And so when I say that we were tricked into studying AGN, I started from massive galaxies and now I'm looking at literature on quasi-stars. And so what we do now is, well, I want to say, we call it now keynote modeling, where you draw 3 circles in PowerPoint. And you say, so we think we have a black hole that's accreting. So we have some BLR and accretion disk around it. And then we have an envelope of dense gas. And I say it's an envelope because the covering fraction needs to be quite high because we see many of these systems. So you cannot have a preferred angle, essentially. And so this is the 2D model or 3D model that we were thinking of. And then you can make very simple implementations of this, where essentially we take cloudy and we run a spectrum through a slab of gas and then say, okay, what does that look like? And that's kind of interesting because what it looks like is this. And you see that, so these colored curves on the right. And what you see is that they can make these very strong bomber breaks actually pretty well. Qualitatively, it looks actually pretty good. In detail, it looks pretty bad if you go to the near infrared. But compared to this, without really doing any fancy modeling, we just take some very basic AGN templates here. We pass it through some gas. It actually does pretty damn well. And so we can do slightly better. It's actually the red line here is where we explore slightly different AGN models, where we make it UV weak, which goes in the direction of super Eddington, according to some people. And that does even better, actually. So what this tells us is that this is not like a final answer or the right model. It's not a self-consistent model in any way. But it tells us that we're actually looking at probably some new type of AGN, and it's actually teaching us something very fundamental about how black holes in the early years. So, okay, we've broken all models, maybe, if you believe it or not. And we say this a lot. I say it a lot as well. It's a great way to get observing time approved or other things approved. But I think we need to be very careful. And especially now as we're, beyond the first few years where we just look at funny objects and try to publish a quick paper, we actually need to be a bit more quantitative about, which models are we actually breaking. In the start, we first, you jump to concluding that everything that the theorists do is wrong, but probably, it's not that wrong. And we also need to very carefully look at what we're actually using for our parameter inference, right? So what are we using to actually infer from the data what these systems are physically like? And the second is, of course, to what extent, right? So there's a big difference in saying, okay, I need feedback to be weaker, or I need star formation to be more efficient. Which is very different from saying, okay, well, lambda CDM must be broken. Only one of these gets you a lot of press, but maybe that's not what we should be chasing. And so we've been working on this in all sorts of angles, really on all the 3 big problems that I showed you. We're now trying to work on quantifying each of these steps. And so part of this work is actually led by Anirudh at the MPIA, who's been looking at particularly this diskiness of galaxies. And because how we infer from the NIRSpec spectroscopy, whether a galaxy is rotating or not, is done by applying very simple models. We assume that the galaxy is a thin disk, and then we forward model it and say, okay, what is the rotation velocity that comes out? But if your forward model makes a wrong assumption, then essentially all your inference and all the conclusions that you draw from it are also completely bogus. Right? And so what Anirudh has been doing is to just make tons and tons of mock observations. So both images and spectroscopy looks very pretty. And then essentially running recovery tests endlessly for all snapshots, for all sorts of galaxies. And here I'm showing you a good plot where you see that for the inferred rotation velocity, actually the average is 1 or the median is 1 with some scatter. So we do, the inference works for galaxies where we might expect it to work. What I'm not showing you in this slide, because I didn't, well, Anirudh's on holiday and I didn't get permission. So it's all the cases where it doesn't work. And where there are actually some biases in, for instance, dynamical masses and VO sigma ratios that we infer that were now trying really to understand, which is needed to actually make quantitative statements about, are galaxies growing more rapidly and to what extent are they growing? The other really exciting avenue is actually in the stellar population modeling. So I showed you before that there are these two solutions essentially, and I said, the blue is sort of the youngest you can push in. But really what lies underneath this is some very fundamental uncertainties in our stellar population modeling. And the reason for this is that our stellar population models were tuned in the local universe. So, based on stellar spectra in a Milky Way, tested on globular clusters, tested on nearby galaxies. But elements that take a long time to form are, of course, present in the local universe, but not present in the higher universe. In particular, things like iron that form, in processes that take a few hundred megayears or about 100 megayears or so. They take time to build up. And so these very high redshift systems actually are not very, well, they're metal rich depending on which metal you're looking at, right? So they have very high magnesium over iron ratios. That's sort of these circles here where Eliza Beveridge did very detailed individual elemental abundance modeling for high redshift Poisson galaxies. But you see that they have very low iron abundances. And so what this means is that actually these different abundance patterns affect the overall SED shape quite significantly. So in the continuum up to sort of 20%. And so that means when you apply your default stellar population model to your high redshift galaxy, actually the parameters you get out are somewhat nonsensical because your input model is simply cannot capture the true spectrum. And so what is so exciting here is actually that MJ Park has recently actually developed these models. It's been really a roadblock for more than a decade now, I would say, where these are alpha enhanced models or also the isochrones. So the stellar spectra and the isochrones are alpha enhanced in a self-consistent manner. And this is something that we're now very actively working on to see how does this affect essentially the star formation history that we infer. Because probably the truth is going to be somewhere in the middle between these purple and blue curves. And regardless of where it ends up, it's going to be a very extreme system, but probably not at the cosmology breaking level. And then finally, as I showed before, for some models, we actually need to come up with something completely new. And this is something that's we're working very hard on at the moment, mostly in an empirical way at the moment. But it's it's I don't have anything. Well, I don't have much intelligence to say at the moment. I think the most interesting part is that since learning that gas can cause this reddening, essentially, we've ruled out that we need dust in these systems. And just by getting rid of that problem, we've already lowered all our bolometric luminosities by a factor of 10 or so. And also, actually, we can reduce our black hole masses that we infer by quite a significant factor. And so this means that, again, this tension that we had before between with simulations and these little red dots kind of goes away once you have a better understanding of the intrinsic physics of the system. Finally, I will say that not everything goes away if you have better models to model your data with. I think there is truly some tension there between, so it is true that galaxies are forming more rapidly. And so there is also some work to be done on the theoretical side. And so some models have been proposed. For instance, this feedback-free model. What this does, so if you look at this is the mass function, stellar mass function, what normal models predict is in gray, and the black are the data points from JWST. And what these colored models do is they essentially allow for these very rapid bursts of star formation that then also immediately shut off the star formation. So these are temporarily feedback-free bursts of star formation that allow you to very rapidly build up stellar mass. And as you can see, these orange curves kind of go through the data points. So there's some maybe. So with that, I'll leave you with my summary, and that is that JWST has delivered amazing imaging spectroscopy and has revealed all these puzzles that we're actively working on. There might be a need to actually revise some of our theoretical models, but it's still TBD to us. I'll just say that a lot of our data, or actually all our data, are fully public. And Gabe Bremer has made this incredible website where you can browse these RGB mosaics. And then you can click on individual galaxies and actually see the spectra as it goes. Thanks. You have to.
Okay, for the Zoom audience, if you can hear me, I'm afraid the questions will be very difficult for you to hear, so sorry. All right, questions in the audience, particularly from students and staff. Earlier. Do you have a question?
Yeah.
Yeah.
Okay. So first of all, the rest of it was really inspiring. I have one question, one inspiration. Maybe let's go with the question. So about the this domination at the hierarchy that you talked about, smoothness, the fact that we are discriminated. But these galaxies are observed in the rest space, they are observed in the optical band, right? So could it be that there is some dust obscuration? I mean, my question is, what happens if we could observe these galaxies in the far infrared? Could it be that maybe we could see a dust obscured large component, and so maybe these galaxies are much less discriminated than what they appear in the optical? So yeah, your opinion about this.
So the question is on the diskiness, whether if we're looking in the optical, whether that's truly a representation of the underlying mass profile, essentially, right? So whether we're biased towards only seeing the unobscured part of the galaxy. I think the answer is that it depends on mass. So for where I say that the disks are surprising, let me see if I can go back to this slide. Yes. So a lot of these systems are actually pretty blue, and they're actually pretty low mass. Okay, there are a few exceptions, but they're pretty blue and actually pretty low mass. And what this means is that they don't actually have a whole lot of dust in their center. And this is something we can measure just, by seeing by quantifying the AV gradients, essentially. And sure, there are some galaxies where there is likely some pore that would show up in the near infrared or maybe longer wavelengths even. For a lot of these low mass systems, actually the dust content is pretty low. And so we're pretty confident that the rest optical probes pretty well the underlying stellar mass distribution. So it actually tells you something about the underlying structure. I think the bigger concern that I have with some of these systems is that very strong emission lines can also dominate. And so what we've sort of fixed that problem by taking a lot of medium band imaging, so you're actually probing a continuum rather than emission. So I think the morphologies are pretty robust in the sense that we really do see these smooth systems, and it's only when you really, really zoom in with strongly lensed objects you start seeing clumpy nature.
Question.
I would like to come to the mass discrepancy. The low mass and they showed that the stellar mass is higher than with the molecular mass. My question is, like this, could it be that these systems in high redshift are simply not dynamically relaxed? So that's polarization time needed to come to the equilibrium, something out there. The early universe was 300 years old. Probably the relaxation time, but we realize it's simply not.
So these particular galaxies are about 1 billion years after the Big Bang, and the sort of the dynamical timescale is really, really short. So you'd expect. So I think the biggest concern in actually getting a dynamical mass from the ionized gas for these sources is actually if you have non-gravitational motions. So I mean feedback processes that essentially drive outflows in these galaxies that are then, essentially bias your velocity gradients high or your dispersions to higher values. So if you infer a high mass that's not there. And this is exactly why we're now actually turning to these hydrodynamic simulations to test, if I have a system that is either merging or has a lot of gases outflowing, how biased is my measurement? I will say that, so for these systems, I fully agree that's a very viable explanation. But the fact that we see this for all systems And actually, well, in the latest figures that I've seen, there doesn't seem to be a very strong correlation with things like specific star formation rate. That tells me that it's might not be actually these non-gravitational motions that are driving this, and could actually just be gravitational in this case. But this is exactly why I say might and could, and have still some question marks. But I think this is partially real, and so this is partially actually driven by gravitational motions, and only some systems are affected by very strong non-gravitation.
I wanted to ask about your the extreme source of Richard 3.5, the one with the
Black hole star.
ray.
Yeah.
If you go back to the spectrum, this thing is missing all three, so typical narrow lines from AGN. So when you do cloudy simulations, do you turn down the metallicity, or is the density doing the trick?
So for cloudy, so yeah, there are two components to the question. Maybe I should repeat for the online people. So the question is that in the spectrum here, you don't see O3 emission, whereas in all these other LRDs, actually, we do see pretty bright O3 emission. And so in the paper, we talked a lot about this, and originally, actually, the name for this source was the POP3 LRD, which then actually renamed at the very last minute because it was too speculative. But it could imply very low metallicity, indeed. It could also be that this is forbidden transition. If you have a high enough density, then actually, the O3 lines become weaker, essentially. We really need deeper data to actually constrain the equivalent bit very well. But to answer your real question, so for the cloudy modeling, actually, we ignore for the most part the emission lines, really focus primarily on the continuum and how that is reprocessed. Because the emission lines are very tricky to get right in detail. For the models themselves, yeah, we consider only very low metallicity, so it's mainly because we consider a very small grid to start with. Because each model takes several minutes to compute. But yeah, this is a major region of interest, actually, to quantify in which LRDs we see O3 and which we don't, and like what that correlates with, because it tells you something about the formation.
Related to this, Anna. So, in your quasi-star, quasi-black hole keynote model,
Yes.
what gives you a constraint on the sizes of your black gas envelope? These galaxies are dry-rushy, the ISM is very dense, the ISM which is dense, I think, like picking on the mission line. So, what gives you the 100 AU kind of picture?
Yeah, good question. It's not very well motivated. So where it comes from is essentially the cloudy setup, which is pretty sketchy. I think it is more of an upper limit. So what it tells you is, if I have a black hole, then how large is my slab of gas roughly that I need to put in front of it to make a spectrum like this? And that gives you order of magnitude size estimate. I would not pin anything down on this number. So, yeah.
You are sensitive to the color in front
Yeah.
of you, right? And so, but this is important for the name, right? The black star, because if this is not 100 AU, but it's simply, 1 particle, it's 5%.
Oh, I would say it's more likely it's going to be smaller. So there's, yeah.
Does this come from? That it has to be small so that you call it black star? You know what I mean?
So the fact that it's like more likely to be small than large is simply to do with how you actually have to form the system. Because to make this very dense gas and to not expel it and to keep it in this nice, structure, I think it makes more sense for it to be small than very large. Otherwise, there's anyway. The name itself, it's not my, we've gotten a lot of comments, let's put it that way. The name itself mainly comes from the fact that, it's sort of cute, it has a nice acronym. It's not, I think, a physical model. I mean, none of this is physically self-consistent, right? But forming such a system that is very compact is pretty hard. And so it seems more plausible that you have something very small. There will be some people that say, actually, this dense gas envelope doesn't even need to be here. You can actually have this dense gas happen inside the accretion disk. And so I've seen some new MHD simulations that do this and actually produce spectra that look scarily like the real data. So I think when I say keynote modeling, this is exactly what I mean, right? Where we draw some sort of say, okay, this is now our intuition, but actually this is not a model and we're now only starting to develop an actual.
Very impressive results. I think also what is very impressive is you made the connection to Jenny Green's colloquium in November, and I think it's been an impressive amount of progress. Can you just give us a big update? I remember from that talk, like kind of the big puzzles and challenges to represent these kind of sources that were no X-rays, no alpha detections, no variability. Does any of this help you to study this source, or has it changed?
So I think the variability has changed, where we now have two sources where, well, one where we see reasonably significant variability, and the other where actually it's Rohan's source, which looks similar to this SUV, which also seems to be varied. So I think that points also to the AGN nature of this. I think that has been a big and then for the X-ray weakness, I think that is still up for debate, where if you really have these very high pollen densities of gas, so 10 to the 26, then you can have any X-ray source behind it, and it will be blocked essentially. But I think there's still people favor essentially these X-ray faint sources. I say this within the back of my mind. We now have one very interesting source is actually X-ray detected. We're not far enough in the analysis to actually show you here. So I think that is still definitely not well understood, right? Other things. I think the key progress since Jenny's talks that we've actually ruled out that there's dust in these systems. I think there's only one person in the community left that thinks it. I won't name them, but the other is that we've actually embraced this dense gas model and actually have made some progress towards understanding what ingredients need to go in it.
Question on black holes. A big question is what the seeds are, etc. This clearly says that black hole accretion doesn't quite happen the normal way. Does this have anything to say about the question of whether black holes early on were able to grow faster or not?
I think that is still. Yeah, maybe I should repeat the question on Zoom. Yeah, so the question is whether we can actually say something about the accretion rates and the seed masses based on what we've learned. And I think it's still too early, where the uncertainty on the black hole masses of these systems at the moment is 2 to 3 orders of magnitude. And I think the key progress is now that we've accepted that our black hole mass estimates are probably wrong. So we cannot, clearly these systems are not like the systems that we based our scaling relations on, so we cannot apply local scaling relations to infer black hole masses for these systems. And so what this actually is telling us about black hole growth, I think the only thing that's telling us at the moment is that there is this other mode essentially that we hadn't observed before. But what the rate is and what the masses are, I think that is completely unconstrained.
Thank you so much for this. My question is, you showed that to get these galaxies, you need to populate the N=2 level of hydrogen, which requires a certain density. I think you've been before anyway. Therefore, you must know something about the in situ pressure of that gas. And my question is, how does that compare with estimates for period equilibrium around two black holes?
That's a very good question.
Might be related also to Hans Walter's question.
I don't have an answer for you immediately. I don't think we've really thought about it from that angle, to be honest. So what I can say is that these quasi-star models were initially invoked to grow light seeds extremely rapidly into intermediate mass black holes, essentially. By having this 3D configuration where you have this outer shell, that's where you have accretion happening from all sides, essentially. I guess the pressure is such that you can actually and have this very rapid accretion phase. Quantitatively, actually, we can chat, but I don't have an answer for you.
That's goes to one.
Yes.
Last. Okay, the speculative one, where are these systems, the local universe? Why do we only see them in speculative?
Yeah, so the number density really drops below redshift 3 or so. We do have actually quite a lot still at redshift 3. And so at some point we need to transition from these sources into normal AGN, right? Because redshift 2 is actually where we see also normal quasars and normal AGN. And so at some point you need to go from one to the other. And I think, so we've now been finding these X-ray luminous, well, we found one X-ray luminous source that helps us the spectrum. We found a few more. And I think those are very interesting because they could tell us something about the transition phase, where maybe you need to somehow blow out this gas through AGN feedback, or somehow it gets destroyed in, say, galaxy mergers or something like that. Yeah, I think it's a very interesting drop. It really seems to be real. Before, people said it drops off below redshift 4, but it seemed to be an observational bias because we just weren't using the right photometry. But I think there is a physical change happening. And so there are still some sorts of redshift 1 and 2, if you really look in wide area imaging, but there really is this transition happening. And how that happens, and you know, that's really something we're looking into now. Yeah, it's for sure interesting.
And thanks, Anna.